Hello, everyone. If there was someone who knew the future exactly, then he would be the richest man on earth. All he has to do is walk into a casino, place all the right bets, and walk out with all the money he needs. Unfortunately, such a person does not exist, and therefore we need to study profit inequalities. Profit inequalities tell you what to do in a casino when you do not have knowledge of the future. The setting is the following. Suppose you have n equals to 5 treasure boxes, and you do not know how much treasure is inside each box or how much reward is inside each box. But having dealt with treasure boxes all your life, you know for each box a distribution such that the actual amount of treasure is sampled from this distribution. For example, for the first box, you may know that the actual amount of treasure inside is uniform between 3 and 5. For the second one, you may know it's uniform between 1 and 9, and so on for the remaining boxes. Now, you're only allowed to take one of these boxes, and you want to take as much reward as possible. What do? Well, the answer is simple. You open all the boxes, you look at what's inside, and you pick the box with the largest reward. This is what I will call an offline solution. It is always the optimal solution. You take all the boxes and you see the best for you and you take that. And I want to contrast this with an online solution. In the online solution, you go to the first box, you open it, and now you need to make a decision. You see it has 4 units of reward. You need to decide whether you want to take these 4 units of reward, in which case the game is over. You don't see what is in the other boxes. Or you can skip these 4 units of reward forever and look at the next box. So suppose you decide to skip. Then you open the second box. You see it has 7 units of reward. Now, again, you have to make a decision. Do you take these 7 units of reward and then you don't see any of the remaining boxes? Or you skip them and then you look at the third box and so on. So suppose you actually take these 7 units of reward, the game stops, you walk away with 7. And then this is your online solution. Now, because the offline solution is always the best, it is always also larger than the online solution. And a profit inequality is just the ratio between the best offline solution and the best online solution. This is always larger than 1. And the field of profit inequalities deals with the following question. Given a set of feasibility constraints, a feasibility constraint is just a set of subsets of boxes that you're allowed to take. So in this example, the feasibility constraint would be the set of all singleton sets of boxes because you're only allowed to take one box. You may consider more general feasibility constraints where, say, you're allowed to take any set of size at most 3 of boxes, and then the feasibility constraints will be different. But for any given set of feasibility constraints, you can define a profit inequality, which is the ratio of the best offline solution to the best online solution, and it's always at least 1. The set of feasibility constraints that we are interested in are those that can be written as an intersection of Q matroids, where Q is a parameter. If you don't know what a matroid is, trust me, even I didn't know what a matroid is before this paper, so it's okay to not know it. We will define it when we need it, but it's a well-defined notion. It's a central problem that we want profit inequality bounds on. A lot of work has been done on it. And for example, we know that if you have an intersection of Q matroids, then the profit inequality is upper bounded by E times Q plus 1. Here, E is approximately 2.7. It is the base of the natural logarithm. And the way I want you to think of this result is that it is a new algorithm. It shows that offline over online is at most this, which means it basically gives you a new online algorithm that gets a large chunk of the offline reward. Okay. If you restrict this to the special case of partition matroids, then you can get even better algorithms. Very recently, it was shown that for partition matroids, which are a special case of all matroids, you have an algorithm that gets an even larger chunk. It shaves off a factor of E, it gets a Q plus 1 fraction of the offline revenue. Again, if you do not know what is a partition matroid, neither do I. It doesn't matter right now. Okay, these are the upper bounds. We also have a lower bound. We know that for partition matroids, the profit inequality, which is the ratio of offline over online, is always at least root Q. And if the upper bounds were algorithms, this lower bound is an impossibility result. It shows that regardless of what your online algorithm does, it can never get more than a 1 over root Q fraction of the offline reward. I'm using reward and revenue interchangeably. They are basically the same terms for us. And this is the best lower bound we know, root Q. The best upper bound we know is Q plus 1. And therefore, there's a gap of root Q versus Q between the best upper bound and the best lower bound. And our work tries to make progress on this gap. We show a better lower bound. Instead of showing Q to the 1/2, we show a better lower bound of Q to the 1/2 plus 1 over log Q, which again also holds for partition matroids. This is our main result. We show that if you have an intersection of Q partition matroids, then your profit inequality is at least Q to the 1/2 plus 1 over log Q. Now, you may complain that this improvement over Q to the 1/2 is relatively minor, and that is a true complaint. But the real contribution of this result is it gives us the right direction to hunt for. We had a gap between root Q and Q that both of them, to be honest, are very natural solutions for the profit inequality. We did not know which one. But with this new lower bound, we now know the direction we have to look in. We know that we should go for better lower bounds first and see how far we can push them, and then maybe try to get the right answer from the other side. So the quantitative contribution is this new lower bound. The qualitative contribution is the right direction, but it doesn't solve the problem exactly. So there's still a gap between Q to the 1/2 plus 1 over log Q, which is what we get, versus ordered Q, which is the best upper bound. And closing this gap is it's a great question that we leave open. This is the main result. Next, I will overview the proof of this result. And our proof follows the framework given by KW12. In this framework, there is a parameter P. There are P to the P groups of boxes shown as follows. Each group has P boxes, so P is 5 here. And each box has unit reward with probability 1 over P. So you get 1 unit of reward. And with the remaining probability, the box is empty and you get 0 reward. Okay. This is the system. The feasibility constraints only allow you to pick boxes from one of these groups. If you want, you can take all 5 of these boxes. That is valid. You can take this box, and this box because they are in the same group. That is also valid. But you cannot, for example, take this box with this box because these two lie in different groups, and that is not allowed. These are the feasibility constraints. And I claim that with these constraints, the profit inequality is at least P. Why is that? Consider the best offline solution. The best offline solution opens all the boxes. Each box is 1 with probability 1 over P, which means a group of P boxes is all ones with probability at least 1 over P to the P. And because there are P to the P groups of boxes, in expectation, there is at least one group that has all the boxes equal to 1. The offline solution will simply pick this group and it will get a reward of P. Okay. Now let us look at the best online solution. The online solution cannot see the boxes in the future. And by our construction, all these boxes are symmetric. So to the online solution, all of these boxes look the same. And therefore, as soon as this online solution picks one of the boxes, it gets locked into the group of that box, and it cannot pick anything outside that group. But as soon as you're locked inside a group, you only have P boxes, each with an expected reward of 1 over P. And therefore, your expected reward is only a constant. So the reward of the offline algorithm is omega P. The reward of the online algorithm is a constant. The multiplicative gap, which is the profit inequality, is therefore at least P. And this is the framework of KW12 for showing profit inequality lower bounds. The only thing missing from this framework is we haven't actually talked about matroids. We have to show that this set of feasibility constraints where you're only allowed to pick boxes from one of the groups can actually be written as an intersection of some matroids. And this will give us new lower bounds. As an example, suppose you can write this set of feasibility constraint as an intersection of Q equals to P squared matroids. Then with Q equals to P squared matroids, you're able to get a profit inequality of P, which is root Q. And therefore, you're able to show a lower bound of root Q on the profit inequality. Similarly, hypothetically speaking, if you were able to write this set of feasibility constraints as an intersection of Q equals to P matroids, then with Q equals to P matroids, you have a profit inequality of P, which is again, or omega P, which is again omega Q, and therefore you get a lower bound of omega Q. Okay, so the fewer matroids you need to write this feasibility constraints is the better lower bounds you get on the original question. And what we actually show is we are able to write this feasibility constraint as an intersection of Q, which is slightly subquadratic, many partition matroids, P to the 2 minus 1 over log P partition matroids. And this means that with Q equals P to the 2 minus 1 over log P many matroids, you get a profit inequality of P. And if you write P in terms of Q, you get Q to the half plus 1 over log Q, and that is our main result. Okay. So this is what we have to do now. We have to write this feasibility constraint, which only allows you to pick boxes from one of the groups as an intersection of Q equals P to the 2 minus 1 over log P partition matroids. And now we really need to define partition matroids. So let me take you on a trip to India and define partition matroids. So you are in India and you see amazing food everywhere, but you're only one person, you can only eat that much. So what you decide to do is you decide that you will take one food item from each Indian state. And as soon as you made this decision, you're now working with partition matroids. You have the universe of all amazing food items in India. They are partitioned by state into various parts, and you restrict yourself to taking one item from each state. In terms of boxes, you have this universe of P times P to the P boxes. For each matroid, you can partition this universe into many parts, and you restrict yourself to only take items from different parts. Equivalently, you only take at most one item from each part. Okay. This is for one matroid. We have an intersection of Q matroids. So we have Q different partitions, and whatever set we take must lie in different parts. Each pair of elements in the set must lie in different parts in each of the Q partitions. Okay. This is what we have to do. And we have to show that there is a way to get Q different partitions such that any set of B boxes that is in one group, which means it is feasible, if and only if this set B lies in all the matroids, which means it is in different parts in all the matroids. Okay. This is an equivalence. So we will show each direction separately. Let us focus on the forward direction. Let us show that if your set of P boxes, set B of boxes is in one group, then it lies in all the matroids. And for this, I claim that it is sufficient to have all your matroids go in a cycle. What does that mean? We say a matroid goes in a cycle if for any group, let's say you focus on this group and you take the lowest element, the lowest as in the bottommost element of this group. If this lowest element is in the second part, then, and you start going clockwise, then the next one is in the third part. The one after that is in the fourth part. The one after that is in the fifth part, and so on. Similarly, for this group, the lowest element or the bottommost element is in the fifth part. So the one after that is in part one, the one after that is in part two, and so on. These matroids that go in a cycle ensure that any set B of boxes in one group are definitely in all the matroids. Why? You pick any set of boxes inside a group, because they are in the same group, they definitely belong to a different part of each matroid. And by definition, because you're picking only one item from different parts of matroid, you are inside the matroid. This holds for all the matroids, and this finishes the forward direction. Okay. In fact, having matroids that always go in a cycle actually gives us a very clean representation of these matroids. Suppose I want to represent a matroid that always goes in a cycle. Then all I have to do is I have to write a sequence of P to the P numbers, one for each group. And the number for group 1 is just the part that the bottommost or the lowest element of group lies in. So we said that the lowest element of group 1 lies in the second part, so we write 2 for that. Here it lies in the fifth part, we write 5 for that, and so on until you eventually write 1 for the last group. And this sequence of numbers uniquely defines the first matroid. You can do this for all the matroids in your system, and then you can define your system of two matroids as a nice vector where the columns represent matroids, as a nice matrix where the columns represent matroids, the groups, the rows represent the groups, which I will also call vectors. These are all vectors. And each coordinate decides whether the lowest item in that group lies in which part of the matroid. Okay, so this is now our system. It's defined by a matrix, which has where the rows are vectors and the columns are matroids. And now in this reformulation, let us see what happens to the backward direction that we still haven't shown. For the backwards direction, we have to show that we'll show it in the converse. So we have to show if you have a set of boxes that do not lie in one group. Let's say you have two boxes, this one and this one, that lie in different groups. Then there is a matroid such that both of these belong to the same part in that matroid. So for here in the first matroid, both of these belong to the same part 3, and we're done. Okay, so what does this translate to when you look at your matroids as these sequences? The answer is the part of this matroid, this box is the first one from the bottommost element. So it is 2 plus 1. This box is the second one from the bottommost element. It is 1 plus 2. And these boxes will be in the same part if and only if the bottommost element here and the bottommost element here differ by 1. So you want 2 and 1, these two to differ by 1. And then you ensure that these two are in the same part. This was for these two specific boxes. In the general case, to prohibit any box from here and any box from here from being selected together, you have to make sure that in this row, which is corresponding to the first group, and in this row, which is corresponding to this last group, and for every element in P, there is always a column such that the difference is equal to that element. Okay, for example, if P is 5, suppose I pick 3, then there should be a column here such that the entry here minus the entry here is equal to 3. Okay, if this is true, then no matter what you pick here, no matter what you pick here, there will always be one column or one matroid such that they lie in the same part, and that is what you want. So I will call this property the property of covering the set P, because for any element in P, you have a column such that the difference is equal to that element. And in this reformulation, you now have to construct a P to the P size family of vectors because they are P to the P groups. Each group should have P to the 2 minus 1 over log P length vectors. Sorry, this family should have P to the 2 minus 1 over log P length vectors because the number of matroids you want is P to the 2 minus 1 over log P. And finally, you also want this family to cover P. For any two different vectors in this family there and any element in P, there should be a column where the difference is exactly that element. So we want a P to the P sized P covering family of P to the 2 minus 1 over log P length vectors. This is the family that we construct, and we construct it recursively. We show two operations, both of which take an n-sized, S is the subset of P covering family, and L length vectors to an n prime sized S prime covering L prime length family. And we will start with smaller families with low covering and get larger families with larger covering. We have two different operations. The first one we call the size for length boosting. And this takes an n-sized S covering L length family to an n square sized S covering 2L length family. And this is done by taking pairs. You take all the vectors in the first family, and these vectors will form n square pairs. And you take all of these pairs and you concatenate them together. Okay, so now your new family has n square different vectors. They are twice as long because they are composed by concatenation. And the claim is this new family still covers S. Why is that? You take any two pairs in this family, there's at least one element in the pair where they're different. And by definition of the original family, this difference will cover S. So the new family will also cover S. Okay, this is the first operation. It gives you more size at the cost of more length, but it keeps the cover unchanged. The second operation will give you more cover at the cost of more length, and it will keep the size unchanged. And this is done by taking an element A, this is an element of P, and you take any vector in the original family and you append to it a version of itself that is scaled by A. So if you started with a vector V, now you have V, and appended to it is A times V. And the number of vectors is obviously the same because you just append each vector to a scaled version of itself. The length is now twice. And the claim is now this family covers S union A of S. Why? Well, the first half of the vector is the exact same, so you obviously cover S. The second half is just scaled by A. So the differences are also scaled. And if you had some difference in S before, you have A times that now. And therefore, you cover both S and A times S. So you cover S union A times S. Now, I want you to think of this S union A times S as really being twice as large as S. It may not be the case if they're not disjoint, but let us assume we are very clever in our choice of A, and this new set is twice as large as the original set. Then in the first operation, you squared the size of the family and doubled the length. The set was unchanged. In the second operation, the size was unchanged. You doubled the coverage and the length also got doubled. Okay. So if you start with a constant size, constant covering, constant length family, and you want to get these parameters, then you first need to apply this operation to get the right size. This will keep the length as a constant. And then separately, you apply this operation to get the right coverage, and this will not change the size at all. Okay. So for the first thing, you need to get from constant to P to the P, which means that you have to square roughly log P times. There is an extra term of log P, but let's ignore that. You have to square roughly log P times. And this will also increase the length by a factor of P. And you get P to the P size constant covering family of roughly P length vectors. Okay. Now you have the right size. So now you start increasing the cover. And each time you do this, your cover increases by 2. And your length increases by the same factor. So if you increase the cover from 2 to P, your length will increase by another P, and you get P to the P sized P covering family of P squared length vectors. This is not what I claimed. I claimed something subquadratic. I'm getting P squared. So how do I reduce it even further to get subquadratic? The answer is to use a result from AA20. What they show is that for any parameter K, if you define L like this, then you can have a 2 to the L sized K covering L family and 2 to the L sized K covering family of length L vectors. Okay. I claim that this actually helps us reduce the number of operations. Why is that? Suppose you apply this result with K such that L, which is K to the log K, is equal to P log P. Then you get a 2 to the L, which is P to the P sized family of P log P length vectors. That is K covering. And because K to the log K is P log P, K is actually P to the 1 over log P. You can do the math. So you get P to the P sized, P to the 1 over log P covering, P log P length family. Okay. Remember, earlier we had a P to the P size constant covering P length family, and now we have a P to the P size P to the 1 over log P covering P length family. Because our coverage is larger, we now need to apply the second operation a fewer number of times. And quantitatively, we need to apply it these many times fewer than before. Before we had log P, now we have at most log P minus omega log P or log P, many operations. And because you have fewer operations, your length will not increase by that much. Each time you apply this, your length increases by a factor of 2. So now you have these many fewer operations, which means you save 2 to the this in the length. So your length, instead of being P squared, is now P squared divided by 2 to the this number, which is equal to this. And this is the claimed result. There are some details that I'm skipping because this family is only promised to do arithmetic in ZK. It's doing arithmetic modulo K, while we want something that does arithmetic modulo P. But you can fix all of these details and you can still get the same parameters roughly. P to the P size, P covering, P to the 2 minus 1 over log P length family. This implies the lower bound claimed on matroid profit inequalities, and that's the whole presentation. Thank you.